Hello. In this video, I'll argue that there is a definite causal relationship between a player's height and his or her free throw performance. That is, when it comes to free throws, shorter players enjoys a natural advantage over taller players, an advantage that is of purely mathematical nature. The fact that shorter players tend to be better free throwers has been observed statistically. For example, in this blog post by a data scientist named Dylan Sivori, we can see that statistically there is a downward trend between the player's free throw percentage and height. The negative correlation, albeit weak, is significant. But currently there is debate going on regarding whether or not the relationship is actually causal. In the same blog post, the author suggests that it may actually has to do more with the player's position rather than the height itself. In another analysis done by two researchers from the Utah Valley University, also finds significant correlations between free throw percentage and height, among other variables. The authors conclude that when wingspan was accounted for, no other variables were related to free throw percentage. In this video, I'll look at the problem from a different angle, a theoretical perspective, and will prove mathematically that shorter players do have an advantage. The mathematics involved are completely elementary. For the most part, it only uses high school algebra and trigonometry. There is a portion in which calculus is used, but it is not absolutely necessary. In our analysis, we'll consider two factors influencing the margin of error of a free throw shot, which are, upon entering the hoop, the kinetic energy of the basketball, and the effective hoop area. These two factors will be simply referred to as energy and area for the rest of our discussion. What does energy have to do with the margin of error? This is our intuition. If the energy is low, in the event that the ball hits a solid object, such as the hoop itself or the backboard, the collision would be weak and the resulting change of course would be slight, which allows for a better chance of scoring. To understand the concept of effective hoop area, let's take a closer look at the moment when the ball enters the hoop. So here we have a diagram. The direction of the yellow arrows is the direction of the entry velocity. The effective hoop area, which is shown as the green segment I'm currently pointing at, is the total hoop area projected onto the plane orthogonal to the entry velocity. This is the area that actually counts. So imagine, upon entry, if the ball misses the exact center of the hoop, not by much, a bigger area would allow for a bigger chance of scoring. Based on trigonometry, we can express the effective hoop area as a fraction called A of the total hoop area. That is, A equals to the sine of phi, where phi is the entry angle. We established that it is desirable to have low kinetic energy and bigger effective area upon entry. The key insight is that there is a trade-off between the two factors. To increase the area, as we can see from this diagram, the ball must come at a steeper angle. This in turn implies a higher arc, which in turn requires a larger amount of energy. And obviously, the area is maximized if the ball's path is vertical, that is, an infinitely high arc. Here's the visualization. Suppose that the positions of the launch point and target are given. Based on these two positions alone, we can construct the line of sight, that is the white line segment, the safety parabola, that is the blue dotted curve, and the so-called optimal arc, that is the arc that requires the lowest kinetic energy upon entry. The optimal arc is tangent to the safety parabola at exactly the target location. The derivation of the optimal arc as well as the safety parabola were presented in a previous video. Link in the video description. The purple curve depicts a general arc. In this picture, this is the arc with a launch angle of 65.89 degrees. In comparison, the optimal arc has a launch angle of 53.02 degrees. And we can see that upon hitting the target, the purple arc comes down at a steeper angle compared to the optimal arc. Now I'm going to let theta, the launch angle, to vary and see what happens to the general arc. We now put forth our central thesis. That is, a shorter player enjoys a better energy area trade-off. That is, a shorter player can achieve a lower energy and a higher area simultaneously compared to a taller player. This is illustrated in our next two visualizations. The main mathematical result is summarized in this brown curve. Given the player's height, which is taken as the height of the launch point during a free throw shot, the brown curve depicts all possible energy and area combinations for any successful shot. The energy is denoted as K, and the area is denoted as A. And the curve shown right now is the curve for a player that is 2.15 meters tall. The blue dot depicts the energy and area combination when the energy is at its minimum. Equivalently, this minimum energy point corresponds to the optimal arc we mentioned earlier. And the brown dot represents a general arc. For example, here, the launch angle is 51.99 degrees. The energy area trade-off curve has two branches, one up and one down. We call the upper branch superior and the lower branch inferior. The upper branch is called superior because by increasing the kinetic energy, which is a disadvantage, we also increases the area, which is an advantage. On the lower branch, however, by increasing the kinetic energy, the area also decreases, which means there's literally no advantage whatsoever to shoot at an arc that corresponds to a point on the lower branch. The upper branch corresponds to all the arcs that are above the optimal arc, and the lower branch corresponds to all the arcs that are lower than the optimal arc. Let's see what happens when I let the launch angle theta to vary. So right now the arc is getting higher. And now it's coming back down. So far we've shown is the situation when the height is fixed. Now let's see what happens to the energy area trade-off curve when I let h, the height, to vary. Now h is decreasing, and we can see the curve, this whole blob, is moving towards the left. Now the reverse happens. See that again? As h decreases, the curve moves towards the left. The blue curve is the path that the minimum energy point traces out as we varies h. And the dotted brown curve is an approximation of the exact energy area trade-off curve when the energy is near minimum. So now let's put two curves on the plot, one for the taller player and one for the shorter player. We want a combination that has low energy and high area. This means the best possible combination corresponds to the point 0, 1. The energy is 0 and the area is 100%. The closer to this best combination, the better. And clearly we can see there are points on the shorter player's curve that is closer to the best combination than those on the taller player's curve. Watch what happens if I decreases the height even further. While doing so, I'm even going to remove the practical restriction and allow heights to be negative. As we can see, as I drag the shorter player's curve further and further to the left, the curve gets closer and closer to the ideal combination. In the extreme situation, the purple curve practically has a right corner near the point 0, 1. Let's look at an animated process. So therefore we conclude that there are combinations on the shorter player's curve that are mathematically unachievable by the taller player. This gives the shorter player a bigger margin of error. That means in order to compete with his shorter counterpart, a taller player has to be more precise and more consistent. This justifies our main thesis. So the rest of the video is all about deriving the energy and area trade-off curve. The mathematics, albeit elementary, can at times get tedious. So I will not read the derivation line by line. Instead, I'll walk through the main ideas and put the details of derivation on the screen. So if you wish to read the details, you can simply pause the video. First, let's look at the assumptions in our model. The basketball is treated as point mass. Thus, any effect due to the spinning of the basketball is neglected, such as the Magnus effect. Also, we ignore any aerodynamic forces, such as the air drag and the air lift. Non-inertial forces are also neglected. These are the forces due to the spinning of the Earth. The distance of a free throw shot is simply too short for any non-inertial forces to be noticeable. And also, the gravitational field is considered uniform. Under these assumptions, the basketball follows a parabolic path during its flight, a fact that I derived in detail in one of my previous videos. Link in the video description. Now let's introduce a few notations used in our analysis. The launch speed is denoted as v. The launch angle is theta. The entry speed is u, and the entry angle is phi. The hoop's position is given by both its Cartesian coordinate xy and polar coordinates r alpha, where alpha is called the elevation angle. Our main quantities of interest are k and a, which are the kinetic energy per mass upon entry and the effective hoop area. K equals 1/2 times u squared, and a is the sine of phi. Notice that alpha, the hoop's elevation angle, corresponds to the player's height in a one-to-one manner. Because for a free throw shot, the horizontal separation x is fixed, that is the distance from the free throw line to the center of the hoop. And the vertical separation y is the height difference between the hoop and the player's height. So therefore, bigger alpha means shorter player, and lower alpha means taller player. And the mathematical problem just boils down to finding these three functions: k as a function of theta, a as a function of theta, and k as a function of a. The last function is exactly the energy and area trade-off curve we've shown earlier in our animations. And after that's done, we wish to investigate the effect of alpha on all three functions. In particular, we are interested in the behaviors of these functions when theta is near the optimal angle, equivalently when k is near its minimum. Therefore, it is desirable to have a simple approximation for all these functions when theta is near the optimal angle. First, we're going to recall some previous results. This includes the results to the optimal arc problem, as well as the solution to the shooting problem with fixed initial speed. So first, the optimal arc is completely determined by the hoop elevation angle. And these four quantities are the launch angle, entry angle, launch speed, and entry speed for the optimal arc. The solutions to the shooting problem with fixed v are given as follows. The idea is, given xy, the target location, the tangent of the launch angle theta satisfies a quadratic equation. So therefore, there are three possibilities, depending on the sign of the discriminant. If v is greater than VOP, then theta has two solutions. If v equals to VOP, then there is a unique solution. If v is less than VOP, then theta has no solution. This is all shown in detail previously, and link is in the video description. So now we're actually going to solve for the function k theta and a theta. Let's first set up the shooting problem with fixed theta. That is, given x, y, and theta, solve for v, u, k, phi, and a. In comparison, we did the shooting problem with fixed v earlier. And here's our solution. The first statement simply states that the target lies on the trajectory, from which we can solve for v. Notice that v squared has to be positive. So therefore, the denominator in the fraction has to be positive in order to have a solution. This turns out to be equivalent to the launch angle greater than the elevation angle. If theta is less than or equal to alpha, then there is no solution. Using energy conservation, we can solve for u. So immediately that gives us k, which is half u squared. Simplifying the expression for k, we can have two equivalent forms. The first form of k looks like this. This is more convenient when we later investigate the relationship between k and a. The other equivalent form is given as this. This is more useful when we investigate the behavior of K when theta is near the optimal angle. We then move on to find the angle phi, which is the entry angle. This is done by considering the fact that the motion in the horizontal direction is uniform, because the only acceleration is the acceleration due to gravity, which points vertically downward. So therefore, in the horizontal direction, there is no acceleration, and the motion is uniform. So we have a relationship, v times the cosine of theta equals u times the cosine of phi. V we already solved, theta is given, u we already solved, so therefore cosine of theta is determined. And here is the expression for the cosine of phi. The area A is defined as the sine of phi. Since cosine of phi is now solved, we can use the Pythagorean identity to get sine of phi. After simplifying, this is the A as a function of theta. So at this point, I can display the graph of k theta and a theta. The blue solid curve is the function k theta. Actually, that's not entirely accurate. This is in fact the dimensionless version of k theta, in which I use the custom unit g times x over 4. This is a constant for the free throw problem, because g is a constant, and x, that's the free throw line distance. Gx over 4 is roughly 11.12 joules per kilogram. So as we can see, the function k has two vertical asymptotes. That is theta equals to alpha, the left one, and theta equals to half pi, the right one. If theta equals alpha, that means the trajectory is exactly the same as a line of sight. In that case, the basketball is shot as if it were a laser beam, which of course requires an infinite amount of energy. On the other hand, if theta approaches half pi, we get an infinite high arc, which also requires an infinite amount of energy. And the minimum energy point is highlighted as the blue point. The green curve is the graph of the function a theta, which of course cannot exceed 1. That happens only when theta is half pi. Notice something interesting. A theta can be 0. That is highlighted as a green point. This happens when the entry velocity is horizontal. I will then change the target elevation alpha, and we'll see that the two functions, k theta and a theta, will get stretched accordingly. And the yellow curve, once again, is a path traced out by the minimum energy point. Then let's investigate the relationship between k and a function on which our central thesis hinges. We first define kappa as a dimensionless kinetic energy per mass with a unit of gx over 4. Namely, kappa equals to 4k divided by gx. So here we have k as a function of theta and a as a function of theta. Eliminating theta will give us an explicit relationship between a and k. These are the steps, and the explicit relationship is given by a times 1 minus a times kappa squared equals to 1 minus tangent alpha times 1 minus a times kappa squared. This is an implicit relationship between a and kappa, and this is also a quadratic relation, because on the left-hand side we can see there is a term a squared times kappa squared that gives a degree of 4. An explicit formula will be ugly, and therefore it is omitted. However, it is possible to transform the variables and get a cleaner relationship, so that it is more manageable analytically, which we shall show next. However, for the rest of the analysis, I will stick to this boxed equation right here, because I'm displacing everything on decimals, which has no problem handling quadratic implicit relations. So here's the transformation. I let r to be the square root of a over 1 minus a. This new variable r corresponds to a in a one-to-one manner, and also it has an interpretation as well. Because a is the effective target area, 1 minus a is the ineffective target area. In other words, that is the total area minus the effective area. So the ratio between a and 1 minus a is exactly the ratio between the effective hoop area versus the ineffective area. And taking the square root gives us the ratio between the characteristic linear dimensions of the two areas. And by this transformation, kappa can be written as 1 plus r squared over r plus tangent of alpha, which is a much simpler looking formula. And this in fact forms a family of hyperbolas parametrized by alpha. We can also use the relationship between alpha and the player's height to get an explicit relation between kappa, r, and the player's height, shown in the box formula at the bottom. So now we've done with solving the shooting problem. Just to check if we got the correct answer, we wish to recover the quantities given in the optimal arc. And it turns out that everything works out, so I will not dwell further on this section. Okay, now that we have the functions in their exact forms, we also wish to know their behaviors when theta is near the optimal launch angle, for which we will develop a couple of approximations. The tool for that is the Taylor expansion. That is, near a point x0, a function can be approximated by a power series, provided the function is analytic. Here, the function f in the general Taylor expansion will be replaced by a or kappa. We will use the lowest degree Taylor polynomial that is not a constant to approximate our functions. So the problem just boils down to calculating the derivatives of a and kappa at the optimal angle theta OP. And this is where things get kind of tedious. So I'll just go over it really quickly. You can pause the video if you wish to verify the details. Here we calculate a prime, which turns out to be non-zero, and therefore we use a linear approximation for the function a of theta. Here's some further simplification using trig identities. And here is the approximate linear relationship between delta A and delta theta. We'll then find the approximation for kappa. This is where the second equivalent form for k theta comes in handy, because only this part of the function, that is secant of theta, times the cosecant of theta minus alpha depends on theta. So we only need to differentiate this part. So this is the expression of kappa, in which f of theta is the part that we just mentioned. We then differentiate f using symbolic differentiation software, substituting theta OP into these two functions, and this is what we get. First, the first order derivative is equal to 0. This is completely expected because we know at theta optimum, the energy is minimized. And the second order derivative turns out to be non-zero. We can then simplify further so that every constant is in terms of alpha. And this is the final expression for the second order derivative. As a result, near the minimum energy point, the kinetic energy is approximately a quadratic function of theta. Let's take a look at our visualization once again. So in the previous graph we've shown, the blue dotted curve is a quadratic approximation when the energy is near its minimum. And also near the optimal launch angle, a theta can be approximated by a linear function, shown as a green dotted line. We can also vary alpha to see how they change. As we can see, they stretch accordingly as well. So now that we have delta A as well as delta kappa, both are in terms of delta theta. We can then eliminate delta theta to get an explicit relation between delta kappa and delta A. And this is the relationship. Delta A equals to plus or minus some constant, which is determined by alpha, times the square root of delta kappa. And that is the brown dotted curve we shown earlier. As we can see, when the energy is near minimum, it provides an excellent approximation of the exact curve. So yeah, that's pretty much it. We have everything we needed, and all the important results are summarized on this page. So that brings to the end of today's video. This is probably the most complex video I've ever made. If you enjoy the video, please consider like and subscribe, and I'll see you next time. Bye.